In Module 2 of Chapter 24, we're going to develop an equilibrium equation for bonds. And it's going to be reminiscent of the Black-Scholes equation. It's going to be a partial differential equation. It's going to look different at first, and we're ultimately going to see that it really is the same. And there'll be a fundamental insight that we'll gain as to why initially the equation looks so different from the Black-Scholes formula, and yet when that equation is applied to a stock rather than a bond, it ultimately reduces to the Black-Scholes equation. There's a fundamental difference between a bond and a stock, and we'll see this in a few minutes. So we're going to go back to this process for interest rates, and now it's going to be a short-term rate. So imagine that R is the overnight interest rate, and we have a model for its process which has some functional drift term, unspecified, some functional volatility term. So this is precisely the same interpretation as for stock prices, except we're saying that we're not going to mathematically or formulaically identify A and sigma as functions. We're just saying they are some function, and right now we don't care what they are. And let's use the notation P of RT. It's the price at time t of a t period 0. And when the short rate is R. So because R is the only interest rate observable in this model, again we're modeling the short rate, we ultimately need to at least formulaically identify, symbolically identify, that the price of zeros should depend on 3 parameters. The day we price them, that's little t, the maturity or the length of the zero coupon bond, that's capital T, and then what is the prevailing short rate, R. That's the only thing it can depend on. And now what we're going to do is apply Ito's lemma to say what in fact will be the stochastic process followed by the price of these zeros. Now notice that in this one symbol, P of R, TT, I'm capturing the price at time little t when the prevailing short rate is R. I'm capturing notationally the price of all zero coupon bonds. So that's the way to think about it. Think about that this formula for a given little t, that's when we do the pricing, and a given value of R, that's the prevailing short rate, this is a function of t. It gives us the collective prices of all zero coupon bonds at that moment. We can apply Ito's lemma by, in the usual way, we need various derivatives of this function, and we need t derivatives and r derivatives, and so the author uses the symbolic alpha and q. And it might be a little bit of a surprise to you that, gee, why is the author using a minus q instead of what you might expect as the variance term of a positive q? Well, we'll see the minus also appears in the definition of q, so it cancels out. This is not a new Ito's lemma, but it's conventional in many works where the volatility term has a symbolic negative in front of it to just indicate or to represent the idea that when interest rates go up, prices go down. In other words, intuitively, the sign of the price change is opposite the sign of the interest rate change. But it's purely symbolic, and we'll see another negative in the definition of Q, which would cancel out, and we would just have, of course, Ito's formula. Nothing new here. And if you go back to Ito's formula, this is what alpha would be. Notice that we have a divisor of the price in both the definition of the drift term and Q. And the reason for that is we want that I have a reason that we'll see in a moment. I would like to express dP in a way that looks something like geometric Brownian motion, namely where this alpha term can really be thought of as a return, and Q can really be thought of as related to the volatility. if I cancel out the p terms, then I can't think of them in the continuous way that I thought of my stock models, where the coefficients of S in geometric Brownian motion gave me the volatility and the drift of the return. So I'm just symbolically defining alpha and Q so that I can multiply them by the original price to make it look like a geometric type Brownian motion. But you'll notice that in the definitions of alpha and Q, in fact, I have a divisor by P. So it really isn't there, but symbolically I want it to be there because it'll help me do the math later. Also notice that I have this Q, this negative in the definition of Q. Again, there's no negative in Ito, and these two negatives cancel out. So these formulas for the coefficients in our geometric Brownian motion-like structure for dP should be easy to verify. They're a direct application of Ito, and again, notice that the subscripts, as usual, denote derivatives. So P sub r is the r derivative of the P function, PRR is the second r derivative, and so forth. So if these do not look familiar, I think it's useful to pause for a moment and, as an exercise, derive these.